In this section, we'll talk about sparse matrices. And I think you're already familiar with the concept of matrices, and you know how to implement matrices, right? So basically, we use the 2D array, okay? And we could use statically allocated memory space or dynamically allocated memory space for the 2D arrays. So no matter how we allocate memory space, we used a 2D array to implement a matrix, okay? But sometimes we don't need that kind of array to represent a matrix, especially when the matrix is really sparse. Okay, so in this section, we'll talk about what is a sparse matrix and can we implement that in a more efficient way rather than the 2D array? So we'll talk about that kind of questions. Okay, this is one way to represent a matrix. Okay, so this is basically a 2D array. So given a matrix, then the 2D array is perfect to represent all the elements. Okay, there's no problem. Perfect. Then the question is, what if a matrix is sparse? And the sparse matrix is a matrix with lots of default values. So most of the elements are just most of elements have the default value, usually 0. Okay, so what if a matrix is sparse? Then this 2D array is not an efficient way to represent matrix. Then what is a sparse matrix? Sparse matrix is a matrix whose non-zero elements are sparse. So look at this one example of a matrix. So in this matrix, we have lots of zeros and we have a few non-zero elements. So in this kind of situations, this matrix is sparse, right? So as I said, most of the elements have meaningless values, usually zeros, or sometimes it could be a default number like -1 or 1 or whatever, usually zeros. And the array representation is inefficient for a sparse matrix. So why is that inefficient? You know, in this sparse matrix, except this a few non-zero elements, all the other elements are zeros. So to represent these zeros, we are wasting 4 bytes usually. Okay, so we don't have to waste these bytes to represent the zeros. Okay, so if we represent these non-zero elements, that's perfect enough. If we use a 2D array, then there is no way not to represent these zeros. Okay, so when we allocate memory space for a 2D array, then we allocate memory space for all the elements in the matrix. And we are wasting lots of memory spaces. Okay, lots of bytes from the memory space. So instead of wasting the memory space, we will use another more efficient way to represent only non-zero or only non-default values. Okay, here's the question. Why do we care sparse matrix? Okay, think about some examples. Okay, usually in the video recommendation systems, or think about the Amazon. Okay, so we have lots of items and we have lots of users. Okay, then based on their behavior, purchasing behavior, we will recommend another items, or based on their movie history, then we will recommend another movies. Okay, then usually we keep a matrix for the watching history or purchasing history. So let's think about the movie. Okay, then on the left side, in this figure, so rows are the movies and columns are users. Okay, then let's say in these numbers, it's like column 0. The first user likes first movie, and first the review score is 15. Okay, and then first user like the 5th movie, like column 0 likes row 4, and the review score is 91. Okay, and what are these zeros? He didn't watch, or he didn't leave any review score for the other movies. Okay, then think about these situations. How many movies do we have in the systems? Like 1 million? Okay, then how many reviews, or how many users actually leave some reviews? So in my case, I left like a couple of review scores in my TV, like 5 or 10. Then other than that, I have 0 score for other movies. Okay, what about the second user? He or she has the same kind of situations. He can leave some review scores to a few movies. Other than that, she or he will have zeros to other movies. So in this case, we have just a few review scores, and other than that, all the elements are zeros, like this slide. And think about Amazon.com. We have millions of users and millions of items, and we buy a few of them. We buy a few of the million out of million items. Okay. So likewise, we have many kind of situations where the matrix is sparse. Okay. Then if it is million by million, then if we use a 2D array to represent this matrix, then our memory space is not enough. So we cannot implement a recommendation system for Amazon.com with our computer, because our computer doesn't have enough memory space. Okay, so we need a more efficient way to represent a matrix. And here is a better way to represent a sparse matrix rather than the 2D array. Okay, so basically we'll use a linked list, but it is a 2D linked list. So basically we have one linked list following this row. On each row we have one linked list. Okay, and then we have another linked list following the column. So on each column we have a linked list. So that's how we have a 2D linked list. Okay. So basically we will represent just the non-zero elements. If it is a zero element, then we will skip. So we have one structure, T matrix underbar node. Okay. So in this structure, what we need is a value. Okay. So in this matrix, in this example matrix, something like a 15 or 91 or 11 or 3, 28, 22, minus 15. These numbers will be represented by the variable value. And next we have a row and col. So row and col will represent the indexes. So for example, the 15, in this example, the 15, the coordinate of this 15 is 0, 0. So row is 0 and the col is 0. What about minus 6? Then row is 2 and the col is 3. And the value is minus 6. Okay. So by value and row and col, we can represent minus 6 perfectly. Okay, then to represent one element, we need one instance of this structure. Okay, then we have to connect all these elements, right? So like we did in the linked list, then we will connect all of these elements with 2 pointers, down and right. So down follows the column. So on each column, down will point to the next one. So for example, if the current node is 15 in this example, so then value is 15 and row is 0 and col is 0. And down will point this 91. And the right pointer will point 22. Okay. Something like that. And what about 22? Then the value is 22 and the row is 0 and col is 3 and the down pointer will point -6 and right pointer will point -15. Good. Then what about the -15? And there is no, okay, let's talk about the -6. Okay, so if it is -6, then the row is 2 and col is 3 and the value is -6 and the down, we don't have any non-zero element below this -6, so it should go back to the header, okay, header of this column 3. And then what about the right pointer? We don't have anything on the right side of this -6, so the right pointer should point the header for the row 2, okay. So do you remember in the 1D linked list we used the header, okay, so we had a header pointer, it points the first element of the linked list. Likewise, in the 2D matrix we have header of the column and we have header of the rows. So we have two directional linked list. Okay, so header, we have two different structures for header and the entry node. So for the header node, we have a down and right pointers, and next points to the next head. Okay, so for example, if it is the header node of column 1, then down will point 11. And actually, this is a little complicated. Actually, header node is working for the header of the column, and at the same time, it is working as header for the rows. So column 1 and row 1 shares the same header node. Okay, so the 11 is on the diagonal, so it's a little confusing. So let me take an example with the column 2 and row 1. And column 2's down will point to 3. Okay, and then column 2's right. Column 2 is shared with the row 2, so column 2's right will point -6. Okay, I think this might be confusing to you, but let me repeat it one more time. Column 2 and row 2 share the same header node. Okay, so col 2 points to 3 with down pointer, and row 2 will point -6 with right pointer. And the next will point to col 3 and at the same time row 3. So we will share that. Okay. And then, in the header node, we don't need the value and the row and the col. Okay. So we assume that all the columns have something. Okay. So we don't skip any column, we don't skip any rows. So we have header node. So basically the number of header node is maximum of rows and columns. Okay, and then let's talk about the entry node. So in the entry node, we need a down pointer and right pointer, and as you can see in this definition, that we need the row and col and value. Okay, so in the header node, we don't need the row and column and value, but we need the next pointer. But in the entry node, we have down, right, row, column, value. Okay. This slide shows a linked representation of a sparse matrix. Okay, so if we draw the linked list, then it looks like this. So it is actually representing one small sparse matrix on the top right corner. So we have only 4 non-zero elements, and the other elements are zeros. Okay, so when we represent a sparse matrix with the linked representation, we need another type of node. So in the previous slide, we talked about the header node and the entry node. And header node is making one linked list. Right? The first header node is pointing the next header node, and the next one is pointing the next one, and etc. And since this one is making one linked list, we need a header node. Okay. So in this graph, on the left top corner, we have one new type of node. Okay, so in this node, we have a number of columns and number of rows. So 4 and 4, these two numbers are representing the number of columns and number of rows. And this one has a pointer, 2 pointers. Okay, so basically we can reuse this entry node for this header of header nodes. Okay, so again, this node, left top corner, this node is kind of head of the header nodes. Okay, but we can reuse this entry node basically. Okay, so let's take a look at the first column. Okay, so as I said, these header nodes are shared by the column and the rows. So that's why we have H0 on the column and the H0 on the rows. So let's take a look at this first column. So from the H0, the down pointer is pointing to 12. I'm talking about the value. Okay, so 12. So 12 is the first element of this column, non-zero element. So that the header node is pointing 12. Okay, and then if we have another non-zero element on this column, then the 12 node will point to that. But in this case, we don't have anything. So 12 goes back to H0. Okay, so the down pointer of 12 is pointing H0 back. Okay, so we have one linked list here. And what about the H0 on the row? So H0 is pointing 11, right? So the right pointer of H0 is pointing 11. Okay, and then 11 doesn't have anything on the right side, so 11 should point back to H0. So the right pointer of 11 is pointing H0. Okay, perfect. So H0 again, so we have the same header node for the column and the rows. Okay, so by this we can represent all the numbers. Okay, so implementing 2D linked representation of sparse matrix is not that simple. It's not that easy. Okay. Next section is doubly linked list, which is a general extension of single linked list. So basically we have two directions. So in the previous slide, actually we talked about the 2D linked list, right? But in these sections, it's not 2D. Actually, it is 2-directional. So basically linked list has a direction, right? From the header node, we move to the first node and second node and third node. Likewise, we can start from the last node and then to the first node. Okay, this is not 2D, but we have a 2-directional, okay, bidirectional. So doubly linked list is quite simple. It's a linked list in which each node has 2 links, as we've seen in the 2D linked representation for sparse matrix. Okay, and one to the previous node and one to the next node. That's the difference. So we have 2 pointers, but one for the previous node and one for the next node. Okay, as you can see in this slide. Okay, let's take a look at this node 26. And 26 is the data, and the prev pointer is pointing the head node, and the next is pointing 56. So in the definition of this structure, we have element as a data field. So the value is the data variable. And then we have 2 pointers, L link and R link. L stands for left, R stands for right. So left link and right link. Okay, so it looks like this. At the bottom of this slide, we have one structure. We will not go through all the implementation of doubly linked list. Okay, so we will not talk about all the operations except just one operation, insertion. So if we understand how insertion works on the doubly linked list, then it's straightforward. Okay, so let's take a look at this one. So basically we want to insert new node between the node and node right link. Okay, so given this node, then the right side of this node is pointed by node right link, node R link. Okay, then the first step is to allocate memory space for a new node, obviously, and then we have to assign the data to the data field. Okay, so let's assume that this process is done. Okay, now we have the nodes in the memory space like this figure. Okay, then the first step is to set the left link of the new node to point the node. So this is the first step. Okay, and then second line, the new node right link should point node right link like this. And then the third step is that node right link left link is pointing new node like this. Again, node R link is pointing the right node, and then that's left link is pointing new node. Okay, and then the last statement says node R link is pointing new node, this one. So the order of these statements are quite important. If you change the order, then it will not work. Okay, let's take a look at the first one. So when we assign the left link of new node, then we make this left link point the node. Okay, there is no problem. And the next one, the right link of this new node is pointing node right link. Okay, it's good. But if we change the order, if we update node R link first, then the second line of this code segment is not gonna work. Okay, so when we handle these pointers, then we should be careful with the addresses. Once we lose an address of the memory space, then there's no other way to recover. So we shouldn't forget, we shouldn't lose any addresses of any nodes. So we have to point that memory space until we change another pointer which was pointing the node. Okay, so be careful when we change the pointers. Okay, so what is the pros and cons of double linked list? So basically, the backward traversal is efficient. Obviously, there is one advantage. Okay, and then second, insertion deletion is possible in constant time, as in the single linked list. Okay, so it means even with the double linked list, still insertion deletion is possible in a constant time. Okay, and what is disadvantage? Obviously, it requires more space and time. It means we need one more pointer. Okay, so we need more space. Okay, and then we need more time. So when we insert or delete, we have to manage all the pointers. Okay, so we have more pointers, so we have to handle additional pointers. So it takes more time. In this chapter, we talked about list. So basically, linked list. And linked list is really efficient to have lots of elements, homogeneous elements. Okay, so instead of an array, then we can have a flexible number of elements. Okay, so this chapter is quite important. In the next chapter, we'll talk about tree, and this tree will be based on something like a linked list. Okay, so we will have pointers, and whenever we add one node, then we will allocate memory space, and then we will rearrange the pointers to point the children.